Um, Hello, everybody. This is the talk writing kernels and herding cats. The name became subtitle, and we changed the name like this morning because I decided that I would like to talk more about writing kernels and less about the second part. But if I have some time, I will get to that as well. Before that, it is the developer track, but just to make sure who is this talk for, it is for ray tracing or computer graphics guys that are interested in low-level details about how we do stuff on GPU. And it is definitely not for artists. We're not going to talk about V-Ray GPU features. We have talk for that on GTC. We have that in our website. If somebody is interested in those, it's very, very easy to find it. Also, this is not about real-time graphics, so we will not go into DirectX, OpenGL, and other real-time APIs, although it still might be interesting for guys that do real-time API stuff, because some of the things that we do are near real-time or interactive, or they have more or less the same approach in the real-time graphics. About me, I'm the lead V-Ray GPU developer for about 2 years now, and I've been in Chaos Group for a while, working on V-Ray GPU and other projects. And also I'm lecturer for the high-performance computing course in the university, the Sofia University, which we held every other year. The course is open sourced. It's available in GitHub, so everybody who can check it out. Also, why do we do offline rendering? There are a few reasons. First, people do real-time API and real-time rendering because they're interactive and immersive. In these cases, you usually have between 15 to 30 milliseconds for each frame, and that's the budget that you have. And to get into that budget, you have to do some compromises. The compromises are often with the quality and also with the workflow that the artist can have. For example, there are compromises beside the quality in the materials that the artist can use, in the geometry, in the way the lights could behave. The artist is supposed to unwrap all the geometries and then bake stuff. And it can be quite challenging to make a good scene looking. Even today, when real-time engines get more powerful workflows, they're still quite limited compared to what an artist could use in an offline render engine. Offline rendering with V-Ray GPU, it can be nearly real-time in many cases, often things between 1 second and few hours in worst cases. On the CPU, there's it could take days. It doesn't really happen these days, but it used to happen in the past. We focus on quality, so the quality, there could be no compromises there. And even more, when you're not really real-time, it doesn't quite matter if the render will happen in 1 second or a second and a half. It is still very important. We still try to optimize as much as we can, but the workflows and the power tools that we give to the artist are more important, because the artist time is way more important than computer time. It is way cheaper to buy more computers. If the rendering happens offline, you can watch it later. So the most expensive thing is the artist time. What is V-Ray GPU? In Chaos Group, actually, we do 3 renders that can work on CPUs. It is V-Ray, V-Ray GPU, and Corona. So V-Ray GPU is completely different render engine than V-Ray, written from scratch, specifically for the needs of the GPU hardware. It shares mostly the same features and workflows as V-Ray, but its goal is not to make it render exactly the same as V-Ray. There will be always differences, for example, in the way Bitmap is computed, or in the power of some of the highlights, for example. And it gets a bit confusing that V-Ray runs on CPUs, and V-Ray GPU can run on NVIDIA GPUs, AMD GPUs, and CPUs. The way we do is we have zero overhead abstraction layer, or you can think of it as emulation, although people usually, when they think of emulation, they think about something slow, and it's zero overhead way to run our GPU code on CPUs. And therefore, for V-Ray GPU, the CPU pretends well enough to be a CUDA device. So we can utilize all the hardware that you have. And also, you can You can run into other accelerators. We don't officially support much, but if there are other accelerators that support OpenGL, it might work not only on GPUs. This is example of some of the work that one of our clients do. This is made the last few months with the latest V-Ray GPU version. And you can see there are shots from quite a variety of different industries. So V-Ray GPU has to be applicable not in a specific industry, but in many different industries. So we'll pick a topic in V-Ray GPU, and we'll go about how do we implement it, why, what we plan to change, how do we change it, what were the problems, what were the solutions. And the topic will be textures. We mainly group textures into two types, bitmaps and procedurals. Textures are a way to associate a color to a particular point in space with UV mapping. So bitmaps are basically, pretty sure all of you know, but they're a table of values, and when you need to see what each particular value is, you just do a table lookup, and whatever is written there, you use it. There is no other computation involved. They can be different formats, and we of course support all of them. Also, it's not quite sure if it's popular in the game industry, but they can have values more than one, and that's useful for displacement or for light texturing. If you have a light, you might want it to be able to have intensities more than one. Procedurals are things that are created by formula. Formulas can be quite simple, like a flat color, return green, or they can be quite complicated. They can be 2D or 3D textures. If you haven't seen a 3D texture, procedural purling noise is a good example. If you have like whatever object, instead of doing, and you don't have UVs for it, for example, you can use the world position coordinates as UV points, and it will still look seamless and without any seams. So how do we do bitmaps? First, we have to support at least three things: CUDA, OpenGL, and x86, 64, and we don't want to limit us to that. In the future, probably whatever happens, ARM or whatever. So the way we do bitmaps should not be limiting us to any kind of hardware. Also, the system that I will talk about, we started writing them in 2009 probably, so they have changed quite a while in the years. And I'll try to go through all of these changes. And I'm running very late with the time already, so I will speed up a bit. So there are two ways to do textures in CUDA. The one is the legacy way, and the other is the new way. The legacy way is called reference textures, where you have basically to list all the textures that you're going to use in the API, like texture A, texture B, texture C. They support out to 128. And then if you want to read those textures on the device, you have to switch manually in having a way to associate an index or something to this texture. So they're very hard to use, they're limited, and not a great solution. Then there are the bindless textures, which are much better. They're available in Kepler in later. When we started, we had support Fermi still. In bindless texture are much better and easier to use. You basically give a texture object. The API gives you back an integer, and then using that integer, you can read from that texture. This is convenient, and it works. The documentation says that it supports practically unlimited and millions of textures. After I designed the whole texture system, I found out it's 8K. I found out the hard way. I've reported back on it, and I guess it's some kind of driver limitation. But this was very, very, very long time ago. So because we had support in OpenGL and Fermi, this wasn't an applicable solution. So instead, we did the following. There is a way to define a 3D texture in the APIs. The 3D bitmap texture works like you have multiple tiles, one behind another. So you have U, V, and then you have as many of these tiles as you like. So what we do is we used to do is to gather all the textures from the scene, split it in small tiles, put it one behind another, and then there is a very easy way to compute for a particular texture, for particular coordinates on the texture, which is the tile that you need. It's not slow, it's very easy. Filtering is tricky though, because when you want to read a particular pixel from a bitmap, you have to read a few pixels around it and then do some kind of filtering. And if you have, let's say, 500 by 500 texture, and you want to read pixel which is at 256, it's exactly on the edge of the tile, and the other pixel is in the tile behind. And this makes very complicated addressing, which you don't want to do because it's expensive. So what we did is basically duplicating the front row and the most, or the bottom row and the most right column. So instead of 256 by 256, we store 255 by 255. We duplicate the rows, and it works. It works well. Like there's very easy. It's very easy to code. Okay. Now, in theory, you can have limitless tiles. In practice, it's not the case. About 8K, it fails. It's not 8,192, and it fails with awkward error like out of memory or out of resources. It took us a while to find, and it wasn't reproducing on the scenes at the office. It was only reproducing on a production scene that we were not able to test with. So it took us a while to figure it out. And the way to solve it is quite simple. Instead of one 3D texture, we can have 4. In our case, 4 worked fine. It is just a bit slower. You just have to do one module dividing, but it worked great. And this was the way we used to do textures in bitmaps in CUDA in the past. There are a few deficiencies. First is that all the 3D texture tiles should be in the same format. So for example, 4 channels, 8 bits per channel, or 4 channels, whatever, bits per channel. And sometimes we don't want this. And I will go into details why. Also, another big problem is that if VRGPU is interactive render, which means that you can turn around the scene, add materials, add textures, see what happens. And if you add new texture, we had to rebuild the whole 3D array of layered, it is like linear memory, to re-upload it. So you add one new texture, we have to gather all the textures, put them in an array, upload them to the GPU. And although it was very parallel and efficient, it was taking like a second or something, and it could be better. In other APIs like OpenGL, there are textures, but almost like back in the days, almost no OpenGL implementation supported them. And even these days, when there is new device and it has OpenGL support, it often does not support the textures API. So, and we kind of wanted to support all OpenGL devices. So we decided to do our custom bitmaps. It's way easier than it sounds, probably. We had few requirements. We had support CUDA, OpenGL, x86, whatever. It should not be measurably slower than using the native APIs. Of course, probably the native APIs could use some hardware for that, but then again, VRGPU does not read a ton of textures. It does way more stuff, so it should not be visible in the profiler. It should not get you should not be able to see it in the profiler, first 10 functions, and then it should not make the rendering quite slower. Like, probably single-digit number might be okay, but and below 5. It has to be fast to update and modify. You have to be able to send textures as fast as you can without having to rebuild any complex data structures. You have to be able to have different number of channels per texture, different number of bits per channel, and also we do want to be able to have level details or MIP maps created automatically on the fly. And I'll get why in a second. Also, there is a thing that in the game developer industry, I see a lot of game developers here, is not quite popular, probably, which is UDIMs and UV tiles, which is basically the texture space goes usually from 0 to 1. But then the UDIMs, for example, give you, they allow you to extend the texture space from 1 to 2 and from 2 to 3 in both X and Y axis. And then each of these new 1 by 1 squares associates a different texture to it. So texture A is used in the unit square, and in the next one it could be texture B, and so on and so forth. And this is very important workflow for artists that we have to support. If you find it stranger, they have very good reasons why. Artists have good reasons. I've argued with them, they have good reasons. Different number of channels is because often applications export, like you get a mask, black and white mask, the application export it as PNG and we load it. Or we have a glossiness map or bump map, and all these are black and white images. Often in the assets you can find them as PNGs. So we want to detect this, that it is actually a monochrome image and we can use only one channel. We don't want to add any additional buttons or settings and asking the other artist to do it. We have to do it ourselves. So in our implementation currently we support 1 channel, 3 channel, and 4 channel textures, and we detect this automatically without bothering with the artist with this. Also, we need to have different number of bits per channel, because for most of the textures, like used for diffuse, for reflection, for whatever, 8 bits per channel are more than enough. And it's a very easy, nice way to compress stuff. But for lights and for displacement, we need to have HDR 16-bit or 32-bit. So that's why we need different number of bits. Okay. So it's like, what you do is probably this. You have some bitmap in some enum with some flux, and probably the bitmap could be as simple as pointer to something with flux that tell you how to interpret it, and then you have the size, because you want to know how to remap how to read in the array. Like this pointer to device memory, that's the tricky part, and it's tricky part only on GPUs. But I'll get to this in a while. Now, it often happens that particular scenes can be infinitely complex. For example, there can be a camera in a room like this, and there can be many other rooms next to it, and the camera will never see the stuff next to it. And the artists do this because they want to do a fly through around the building or stuff like that. So we don't want to load textures that are not going to be used. But it's quite complicated to find what will be used, because this is not a simple first-time calling. Because in ray-traced graphics, the rays can bounce behind the camera to get the GI or reflections or whatever. So there should be a way to find what textures are actually going to be needed. And this makes it much harder. Like, this makes it times harder, because if you start the ray to bounce around and then you find that a resource is needed, you have to go back to the host, prepare the resource, and send it back. But what happens with the state of this ray? Like, it went into somewhere, so we can either ignore that it went to somewhere and restart it from the beginning, or try to somehow dump its current state in the global memory, then read it later. And also, we know how. Do I have a slide there? Yeah. We know how far away is the texture, and we can project it back to the camera, and we can see what part of the texture projects onto the camera. So we can, instead of loading the texture at full size, we can create a smaller version of it, or multiple smaller versions of the textures, and then blend between those, depending on how far away it is. This sounds like it's something that we do only to save memory. But the reason first it works is that when you have a texture and you shoot pixels through the camera, rays from a particular pixel from the camera might hit different pixels on the texture. And effectively, what this does is that as you shoot more and more rays, you filter a particular part of this texture in the pixel. And what you can do instead is pre-filter the pixel by scaling down the texture. So when you shoot a ray from the camera, you read exactly the same value, or almost exactly the same value that you would if you had filtered the texture from the camera rays. So we have ways to compute them, and this also makes the rendering faster, because you get the filtered result immediately, and you also spare some bandwidth because you do less reads. And most importantly, it saves a lot of memory. Okay, so we do this. We start rendering without any resources loaded. We have a mode in VR GPU that can do this. It's called on-demand bitmap loading. The rays start to bounce around. We find which textures you need. We find how far away they are. We load the appropriate size, the appropriate bitmap with appropriate bits per channel, with appropriate numbers of channels. Oh yeah, and we do this for all texture formats, like PNGs, JPEGs, whatever format, HDRs. It works just automatically. Now, there is a particular problem is that very often you have objects that are very close to you. Like imagine that there is a render of a floor and the floor has like 16K by 16K texture. And then because floor is very visible, very close to you, you have to load very high, very big resolution because it has to look nice, but you don't actually need it all the way. And this happens like, we can't ignore this problem in V-Rate 3.5 where we introduced it, but now we fixed it by, when we detect that a texture is bigger than a certain size, we internally split it into tiles. So every tile can have a different bitmap level, and this is also transparent from the user. For example, so when you take a picture, the tiles that are closer to you, they will be higher resolution, and in the back that will be with lower. But because we compute the proper resolution, you cannot tell that the tiles in the back of the floor with lower resolution. Like it looks almost exactly the same. And this is a case where you might need like more than 8K textures. So if you have 100 textures and you want to divide into 156 tiles each or whatever, you easily get tens of thousands of texture objects or however you call them. And yeah, this is implementation details. It's basically a huge if-then-else statement with more if-then-else statements in it. It's basically if this flag and that flag that I have to, and because V-Rate GPU internally works only with float force, it's RGB and alpha. Every texture read has to be RGB and alpha, and if we read single channel texture, then we have to copy it to the other channels. Yeah, the compilers hate this source. I suspect it's mainly because of the many reads to global memory. And usually this is the thing that broke the most compilers in our code. We have reported bugs to get the proper fixes, but until then, the usual fix when you have a compiler problem, add an inline function, hope that it will work. It worked. So yeah, I've already said this, but here we can see a result of this. These are 370 textures. Of those, 200 are 60K textures with 344 million polygons rendered on a single NVIDIA GTX 970 in less than 3.5 GB memory. And these are real models. Like the camera will go very close, and you will be able to see like it lags because of the video, but you can see that in the piano there is everything's high modeled and textured, and it's true for all of the objects. And this will not be possible without it. Another thing is when we switch from the 3D texture to the on-demand loading with our custom-made bitmaps, you can see the models look practically exactly the same, and we have like near 7-8x reduction in the memory consumption. Is from 2.6 gigabytes to 0.3 gigabytes. So what we have to improve is it is an only page in mechanism. So it means that it continues to load stuff. But what happens if there's no more memory? And a good solution would be just to throw away the least recently used tiles and leave the mechanism to figure out which tiles it will need. We have to do more experiments with this, but this will be an easy way to make page in and page out mechanism. Oh yeah, and I told you that the void star data is tricky, and that's mainly because of the OpenGL. In the standard, they have like this thing that says that you cannot have a pointer to pointers passed as kernel arguments, which means that if you have a pointer to some random OpenGL memory, which is somewhere in a struct that or hidden in a buffer that the driver cannot see passed in the kernel arguments, it might not work because the driver makes sure that although you have allocated the buffer on the GPU and it returned success, it makes sure that only the buffers that are seeing the kernel parameters will actually be on the GPU when you call the kernel. And it makes sense, but it makes programming so much harder. Like, we don't really know how to do ray tracing without pointer to pointer. So we just use them, and it happens that but one OpenGL implementation on one particular operating system supports them. I can get into more details later if you like to know what's the problem. Also, there is no way to get, oh, okay, there are 2 implementations on 2 different operating systems, at least I know probably more. I just remembered one more. And there is no way actually to get the device pointer. No, there is no API. In CUDA it's easy because you can just take it from the host API. On OpenGL we launch a fake kernel with the only job to get the pointer and return it as a result. And then we transfer over the PCI what the actual pointer is. This happens very rarely when you start the scene, but it's like a weird way to do it. We know it's not OpenGL 1.2 standard compliant. With OpenGL 2, I think this might be fixed, but we still haven't gone into that. And this does not work in interactive, our on-demand does not work on interactive rendering. There are no reasons for that, we just haven't made it yet. So, the funnier part, procedurals. So having a formula or algorithm that generates colors. Why you want to use those? They're super powerful. Of course, this what you see in the right is all made with procedural textures for bump mapping and displacement and material parameters. They can be simple, as return some color. They can be complicated. Noise function generators, color corrections, and also if you have bitmap read, and then you do color correction, the color correction makes the entire chain of textures procedural because it is not only simply reading from a bitmap, it is reading and then applying some formula, which means it's procedural. And there are like random generators, stuff like mood texture, forest color is super powerful and cool. But it makes sure that the random is distributed in very nice ways for forest and stuff like this. It's a very complicated thing. There we also have these user attributes, which allows you particular texture to be loaded from a different file depending on which object it is attached to. Or it is even a bit more powerful than that, but it's useful, for example, if you want to make a stadium and there's a lot of people, you want to have different clothes on them. This is stuff that people do with procedural textures. And you can see that they can very easily, in the host application, create a ton of different variations on stuff without having to go to bake them or whatever. They can even use like scene-specific information, like what's the angle between the ray falls on the surface. And then you can make effect that on the edges or on the round shapes, some things appear more different than it appears on when the ray hits it perpendicular, for example. And there's a bunch of stuff that people can do. Yeah, and they can go as deep as the user wants. Procedural texture can be input for another procedural texture, and this can continue for a while. Also, we have like complex texture like ambient occlusion, which is ray-traced ambient occlusion, which can be used anywhere in the procedural tree. For example, you can blend between 2 different materials, 2 different BRDFs, using ambient occlusion texture, which radius can be coming from a triplanar texture, which projects noise and bitmaps and whatever. It usually ends up looking something like this. This is in 3ds Max from a real user production scene. Each of these nodes can be very, very complicated piece of code. It can be very complicated to compute. And this has to run interactively or near real time. And there's another example. Why people do it? Because they can make stuff like this, and this is all procedural textures and materials, which means that if you take this material from this robot and you put it on another object, it will still look fine, because it did not use any unwrapping or whatever. So this is a universal material, you can take it, place it somewhere, it works. Not sure if you can see, but it has a lot of scratches and imperfections, and all those are modeled with the procedural textures. And yeah, of course, more it works in animation, of course, I had to show it. Now, how this is implemented, it is non-based system, so it is quite easy to do on CPU. You just make a texture interface called getColor or whatever, and then you inherit from this interface and you implement each of these textures to behave the way you want. Then you can put as many as you like, one after another. For example, this would be the implementation of a checker texture. You have the white texture or the black texture, as we call them, so texture A, texture B, and then depending on the UV coordinates, we return the first one or the second one. And this works. This is how V-Ray does it internally, the standard V-Ray CPU version. Okay. And Bitmap, it also can be implemented with the same interface. Like this is very, very simplified version of Bitmap, but you get the idea. You just read from a table, you return the result. Few observations that we can make that will be useful later is that most of the textures are flat covers. They're not like the V-Ray material there. It has like 15 mappable parameters, and very rarely more than 5 are mapped. It still can happen, so we have to support it, but it does not happen often. Yeah, we can, one could think that we can try to do crazy stuff like, because there are, the location of the texture objects are aligned, we know there are at least 4 bytes at the end, we can store in the least significant bit if this is a flat texture, and therefore we can spare virtual function call, which, if you imagine all the deep network of procedural textures, there's a lot of function calls, and if you imagine the billions of arrays that's cut around tens of times in a second, it's a lot of function calls. We don't do this on the CPU yet, but we do it on the GPU, and I'll get into that. Why don't we don't use this node-based object-oriented style on the GPU? First is when we started, GPUs did not support function calls, so quite limiting. Virtual functions are function calls. Also today, even though they support them, they're still quite slow, and not all GPUs support them, and not all APIs support them. Okay. So, of course, we implemented a virtual machine that runs every time when a ray hits an object on the GPU, and it runs like 20 times every time when you hit it, because it has like 20 mappable parameters. It is a very high-level virtual machine. Before that, of course, if you don't know, a virtual machine is something that emulates a computer. It can be general-purpose computer, or it can be domain-specific. Like there are virtual machines that can do only specific set of tasks, and it can be very low-level or very high-level. Not like the low virtual machine. It's like they can have instructions that can be quite complex or quite simple, and it depends how you approach the problem. Now, so we have this, we decided to try to do a virtual machine on the GPU, and we start to make sure that we can compute different textures. So we have a stack-based virtual machine. We decompose each procedural texture in one or more virtual machine instructions. And the way it works is that each instruction pushes exactly every time, guaranteed, one value to the stack. And each instruction is allowed to pop 0 or more values from the stack. It's like every stack-based virtual machine ever. So this can sound a bit weird if you're not familiar with this. How can a virtual machine help me to compute this procedural texture stuff? And here's how. This is the checker example from a while ago. The instructions are, you can think of them as linked list, and the virtual machine goes one instruction at a time. So we have color A, color B, checker. So first it will push color A on the stack, and the flat color texture does not pop anything from the stack, it just pushes it. Then the second instruction, we push one more to the stack, and then the checker instruction knows that it is allowed to pop 2 stuff from the stack, because it's hard-coded that it can do this. So the texture instruction pops 2 stuff from the stack, and then it decides, based on the UVs, which one of the A or B it should push. And that's how you can do it with virtual machine. And this allows you to have checker in a checker in a checker. It all will work fine. You have checker with black and white, and the black can be another checker, and you can go, you get the idea. Yeah, our virtual machine is very, very high level, which means that read bitmap is one instruction, generate noise is one instruction. Almost mapped to almost every texture is one instruction, or less than 6, let's say. We have plenty of textures that more than one, but they're not like hundreds of instructions. The instructions are very big in terms of size. They can be, I had to check, it's like a few hundred bytes probably. So it's quite expensive to get it, to read all this and pass it through like a low bandwidth. It's not a general purpose virtual machine. It is not Turing complete or anything, and it's not meant to be. This is the backbones of the implementation. It's basically a stack, an infinite loop that goes to all the instructions. It's not really infinite, a loop that goes through all the instructions. And then we have a big switch statement that does whatever you want it to do. Like you can see, we always push one thing to the stack after the switch, and in the switch, the textures are allowed to pop 0 or more stuff. And the checker basically pops B, pops A, checks if it should use A or B, and pops whatever it has to. That's how checker works. And the result, of course, is on top of the stack. Now, problems. Calling functions, or especially these big, complicated functions on GPU is terribly slow. There is something called register usage, which means that if you have a huge case in this switch, and then you have a small case, because of the SIMD way that GPUs work, you use as many registers as the biggest one uses, which effectively means that it makes the computation slower. So it's stack-driven, and we'll see if this is the best approach possible. So we have used the Mike Acton approximator. Before, it was a cool tweet like a few months ago, but we used it way before it was posted. So first, can we not do this at all? Yes. Can we not do this? Yes, we can. For example, we know that many of the textures are flat covers. Like most of all of them will be. So we have this like we have flag that we check if the texture is a flat cover, and we encode it in only 1 bit. And then most of the calls to the virtual machines are just if statement and a return statement. And if the GPU supports no-inline functions, the other is hidden behind no-inline functions, so they're not inlined everywhere, and this really helps a lot. Number 2, can we do this only once? Of course. We found that a lot of procedural textures do not depend on the ray context or the ray state. They are, for example, a flat cover with a gamma correction. Now, why people do flat covers with gamma corrections? Cannot they just compute what the flat cover values should be? They can, but it's about the workflow. They have like scripts that go and add the proper gamma at the end of each texture node when they know they're done with. It ensures that if you have a studio with many guys, it can ensure that everybody works with the same gamma. So we happen to have like color and then gamma. And we have to call the virtual machine, we have to go to the stack and stuff like that, and this makes it slow. So basically what we do is we run the virtual machine that runs on the GPU before we send all the texture instructions on the CPU, and we should detect that all the instructions know if they depend on stuff that are not only runtime. So basically we pre-compute this stuff in advance if that's possible. And then this gamma of A is also a flat texture, like it's simple color, so it does not require to run the virtual machine again. Now, register usage, and when you have big functions, small functions, so number 3, can we do this fewer times? Yes, often. Often we can approximate good enough what a texture value is, and we can kind of calculate what the coverage of the point we hit, or how important the point we hit is to the viewer. And then we calculate if we can use an approximation or the real thing. We can do this quite rarely, unfortunately, but still, sometimes when we see that a particular ray is not important, we can kind of guess the proper values that will make the image look kind of the same, or completely the same. Oh, I'm going very good with time. That's great. Now, case study, layered texture. Layered texture in Max. Or probably every layered texture ever. A layered texture is basically a list of n textures that you have n layers, and depending on the UVs of the hit, or depending on something else, the renderer picks 2 of those layers. You have A, B, C, D layers. The renderer picks between 2 of those, depending on where you have hit, and it blends between those layers with some blending function that is predefined. Can we do this with the virtual machine? Of course. We have to push. We can push all the layers of the layered texture to the stack. Then we can compute which one we need. We can take them, throw everything else away, blend with them, return the result. It's perfect. The problem is that we find that there are guys that use like 10 ambient occlusion ray traced textures inside the layer texture, which means that we have to compute all 10 of them, throw 8 away, and then use only 2. The question is why you need to compute at the same point 10 different ambient occlusions? And the answer is because they're mappable. They have parameters. They have different radius. They have different bias. It's a very powerful ambient occlusion texture. It's not like a simple one. They have different radius. They can be mapped to different textures, on and on. So it's not a good way because ambient occlusion to compute ray trace specifically is so hard and so expensive, and then we just throw it away. So yeah, this is how it would look like in the naive approach. Push the first texture, push the second, push the third, pop 3. This is the case of 3 because I can fit as many on the slide. And of course, this push A, I've written it at a single instruction, but it can be multiple. It can be 100. So it can be like terribly slow and long process to go through all of them. And it most often is. So we have start layered instruction and end layered instruction. Basically, what we do is that the start layer instruction computes between which 2 textures it has to blend to. And then instead of having instructions for A, B, and C, we have all of them duplicated in pairs. So we have for AB, then we have from BC, then we have from CD, and then from DE, and so on and so forth. And also the first instruction knows the offsets to which it should jump in case it needs these 2 pairs. So for example, in this case, the start instruction can see that it needs to blend between A and B, and that it knows what the offset is to jump to exactly this pair of A and B's that it needs. And if it needs to blend between B and C, the first instruction knows how to make you can think of this as a program counter. It knows how to move it to go to the appropriate place. And then every 2 pair ends with a link, which is basically an offset to the end instruction, which will pop only 2 colors from the stack, only 2 colors that needed, and will blend with the proper functionality. So this way, when your first instruction knows where it has to go, can compute it. The only problem with this approach, it's kind of complicated to get all the offsets right because they get very nested, one in another. Also, the first instruction has to know where it has to jump, where the next instructions are, and this is limited in space. That's why we support, I think, 6 layers in the layer system or something like this. We have just as many values to store, and we cannot allow to make it infinitely bigger because this will make all instructions bigger. We have some ways to alleviate this. We have a way like to use a pointer to device memory and do stuff, but we do this rarely. There's a way to alleviate it. But we have to support the V-Ray API. The V-Ray API is with virtual functions and like texture interface. How do we get from texture interface to something that the GPU can run? So we have a new interface. It's a V-Ray GPU texture interface. And basically what it does, we have domain-specific language that we serialize the textures in a way that it will allow us later to create instruction list, linked list of instructions. So for the checker, it will be call the get source, call the get texture source of texture A. Now I want a new instruction starting. Call the texture source for texture B. Now I want a new instruction starting. And then I am instruction checker. This basically will dump a string that we can go and read. It's also useful for other stuff. And for example, it happens because of how modular and powerful the workflows are. Often there to be a texture there's no need to be procedural, but it just happens to be so. For example, this is an artificial example, but if the texture A is like the texture B or exactly the same, there is no need to compute procedural, like to start the virtual machine at all. And we can detect this even here. It's very, very early stage. We're still on the CPU. It's basic string operations, and it's like the GPU has not to worry about all this. And we do this. Like there are cases where we check if this are the same textures. We remove the procedural texture calculations. So the workflow is we have a V-Ray texture. We call serialize or get texture source. We get a string. It's like XML, but it's not really XML. It's something that we just wrote for the way it's going to be easiest for us. Then we get this string. We parse it. We generate a list of instructions. Then we run free optimization passes like constant propagation, whatever. It kind of looks like a compiler, but it isn't. And then we transfer this list of instructions to GPU. We run it. Everything works. This takes like, if I open a scene and I show how fast it changes, it's like a millisecond or something like. It's like super fast. Also, when you update material or texture, we only regenerate it for the things that changed. So it's like there's a lot of. It seems like a lot of work, and the computer has to do a lot of stuff. But in practice, it's super fast. Another thing is that these days you're able to use a procedural texture that allows you to run your own shaders, like GLSL, MDL, and OSL. At the moment, V-Ray GPU already supports GLSL and MDL. We support GLSL for textures and MDL both for textures and materials. The way we have implemented it is basically the MDL texture or the procedural, the GLSL or MDL texture. They're part of the virtual machine. We have instruction which says, here we call some external thing that does stuff. And when you write a GLSL texture or MDL texture, we have something that gets this source, compiles it to PTX, which is the NVIDIA Intermediate Representation Language. Then we stack the two PTXs together. Then we create binary on the fly on the user machine. Then we run it, and it somehow works. It actually works very well. So, can we replace all this now when we have this and with function calls and GLSL, for example? Probably. Is it going to be fast? We don't know. It probably is going to be the same or something like this, but we still don't know. Yeah, and because the compilations can get quite complicated, the feedback can get worse, but like because you have to wait to recompile on the user machine. But and the biggest benefit of this approach is that it runs a real compilation, which means that it runs the ALVM optimization passes, which are crazy good, and you do great stuff, great job. The best part is that we've tried to get our generated strings, which we used to make a list of instructions, to see how hard it is to change the implementations of those instructions to be modular part of code, which effectively makes it so that instead of creating a list of instructions, you generate GLSL code. And it turns out it's super easy. So like few days of work, and then now we, instead of generating instructions like this, where it turns out to be good that we have all the textures in V-Ray, which are hundreds and hundreds of, few hundreds at least, procedural textures, we can serialize them in a thing that we can then deserialize, and a thing that GPU can understand. So now, instead of doing instructions for a virtual machine, we can generate code and run this and see how fast it is. Now, the question is, what's the best approach? And the answer is we still don't know. It is R&D and the moment, and we have no definitive answer for this yet. That's it.